Welcome to the deep dive. Imagine trying to find your way around a completely new city, but instead of, Google Maps or something, all you've got is this messy pile of notes. Just snippets of conversations, maybe directions someone gave you, like, oh, the bookstore is about a block north of the cafe, or turn left at the park, go straight for a bit. Whew, could you, just from those scattered bits of language, piece together a mental map and actually, navigate effectively? Well, that's the really fascinating question we're diving into today. Can large language models, LLMs, actually learn to map the world and navigate it using only these kinds of local, fragmented language descriptions? No visuals, no GPS coordinates.
Yeah, it's a great question. And our source for this deep dive is a pretty groundbreaking new research paper from arcv.org. It's titled, Can LLMs Learn to Map the World from Local Descriptions? The authors are Siri Shia and colleagues from Fudan University and ByteDance. So our mission for you today is basically to unpack the frankly surprising capabilities these LLMs seem to be developing. We'll dig into how they take this fragmented language and somehow turn it into structured spatial knowledge. Where do they really shine, and what are the limitations still? Where do they stumble? It's kind of a journey into how AI might be building its own internal models of the world and what that could mean down the line for you.
Okay, let's get into that. The core idea.
Yeah.
It's whether LLMs, which we know are brilliant with language, right? Can they go beyond just processing words to actually forming a mental map, a map of a physical place? And the key thing, as you said, no visual input, no explicit coordinates. How on earth did the researchers even set up an experiment to test that?
It's actually quite an elegant setup. They created a simulated urban environment. Think of a big grid, 100 by 100 kilometers. Roads only run horizontally and vertically like a grid system, and each grid square is 1 kilometer. And then they scattered 10,024 unique points of interest POIs randomly across this map. Things like home, school, mall, zoo. Then they generated the key data. Two main types for the LLM. First, what they call the relational spatial data set. This was all about pairs of places and how they relate. So a piece of data might literally say the distance from home to school is 1.4 kilometers and the azimuth is 135 degrees. Or maybe the distance from mall to zoo is 2 kilometers and the azimuth is 90 degrees.
Okay, hold on. Azimuth, that's like the compass direction, right? Relative to north.
And exactly, yeah. Bearing or direction.
So they're essentially feeding the LLM millions of these tiny little verbal clues about where things are relative to each other. They trained a model Pepper, on this stuff to see if it could develop spatial perception. What happened? Did it just memorize the examples, or did it learn something more fundamental?
That's the crucial question. And no, it wasn't just memorization. When they tested its ability to predict the distance and azimuth for unseen pairs of POIs, ones it never encountered in training, the results were, remarkably strong. They used a standard 80.2 split train test, and the model achieved a mean relative percentage error of only 0.11% for distance predictions. That's tiny. And only 0.79% error for the azimuth, the direction.
Wow, okay, 0.11%. That's incredibly precise. Does that mean it really learned the layout? Did it get better with more data?
Absolutely. It showed a powerful ability to generalize the spatial perception from just those local relative descriptions. And yes, definitely, the more data it saw during training, the more accurate it got. There was a very clear learning curve. It was genuinely learning to infer the spatial relationships.
But here's the big question for me. Is it just becoming a really good predictor, like a sophisticated parrot? Or is it actually building some kind of internal representation? Something like a map in its, not head, but you know what I mean.
Yeah.
How did they check that? Did they look inside the model somehow?
They did. They probed what's called the model's latent space. That's sort of the internal workspace where the LLM processes information. And they found that the representations in this space, the way the LLM thought about each TOI, effectively captured absolute coordinate information, the actual X and Y positions.
Wait, really? Even though it was never given coordinates? How could they tell?
They used a small helper network, an MLP probe, basically to try and predict the X and Y coordinates just by looking at the LLM's internal state for each POI. And the predictions were astonishingly accurate. They got R-squared values, a measure of correlation around 1.00. That's almost perfect. And the mean absolute errors were tiny, meaning the predicted coordinates were extremely close to the real one.
Okay, that is an aha moment. So it's not just juggling relative distances and angles. It's actually figuring out where everything is on a global map. It's building that map internally. That feels significant. What does that tell us about LLMs beyond just language tasks?
Well, it strongly suggests the model isn't just learning local facts, but internalizing a coherent global spatial structure with pretty precise absolute positioning baked in. And what's more, the spatial layout within that latent space closely mirrored the actual physical geometry of their simulated city. They checked this using things like Spearman and Pearson correlations for both distance and angle consistency, and they were high. And here's a key part. They found you could figure out the relationship between two POIs just by mathematically combining their individual internal representations. So it points to a really deep, structured understanding, not just surface-level mimicry. It implies these models can potentially build quite sophisticated internal world models just from language.
Okay, so the LLM can build a surprisingly solid mental map, it seems.
Yeah.
But can it use that map, like actually figure out how to get from A to B? Can it navigate, or is it just good at knowing where stuff is?
Right, that's the crucial next step. And that's where the second part of their study, spatial navigation, comes in. For this, they created a different data set, a trajectory data set. This data set had multi-step instructions in natural language describing the shortest path between 2 points. Something like, start from home, go south along Road R5, then go east along Road R3, then arrive at school.
Ah, okay. So it's like giving it turn-by-turn directions, the way you tell a person how to get somewhere. So they trained a different model nav, on these routes.
Yeah.
How did it do when asked to plan paths for pairs of places it hadn't seen a route for before? Did it just memorize paths again?
No, again, it showed really impressive generalization. They had this test called bridged exposure. This means some POIs might have only appeared as starting points in the training data, or only as destinations, but never both. So the model couldn't just memorize a direct route involving them in both roles. And even in that tricky setting, the model achieved an 83.63% exact match accuracy in predicting the shortest path.
83%. Wow. So it must have figured out the underlying road network, the connections, not just the specific routes it was shown.
Exactly. It learned the connectivity patterns, the rules of the road in their simulated city, and interestingly, they found what they called an emerging ability. The model seemed to use its earlier spatial layout understanding, the map it built in the first part, to help it navigate better, especially in completely unseen regions of the map. The model that had been pre-trained on the spatial relationships did significantly better in new areas compared to a baseline model that only learned from the routes.
So the two skills reinforce each other? Knowing the map helps navigation, maybe?
It seems so, and it even worked the other way around, to some extent. They found that even when a model was trained only on the navigation trajectories, its internal latent space still ended up encoding some degree of absolute coordinate information, much better than an untrained model anyway. So just learning how to get places also implicitly helped it build a spatial understanding.
Okay, this is getting wilder. And you mentioned something about knowing where it is during navigation.
Yes, this was another fascinating bit. They found the LLM could dynamically recognize and sort of update its current position while it was generating the navigation steps. They could look at its internal hidden state at each step of a predicted path and accurately extract the absolute coordinates of where the model thought it was at that moment. They called it dynamic spatial location cognition.
So it's not just planning the whole route up front. It's like it's virtually moving along the path and keeping track of its location step by step. For you, the listener, this feels like a massive leap. It's moving towards AI that doesn't just know facts, but can situate itself and act within a spatial context, like for robots or autonomous cars, perhaps. Okay, these results sound, well, almost too good to be true sometimes. Like LLMs could be the ultimate GPS, right? But what happens when things go wrong? We all know GPS sometimes gets confused by a sudden road closure or if you take a wrong turn. How robust is this LLM navigator? I remember my old sat-nav trying to send me into a field once. Does the LLM handle unexpected problems any better?
Well, this is where the study throws up a pretty significant caution flag. The research highlights that the LLM's spatial navigation, quote, remains fragile when faced with unexpected changes or perturbations. They specifically tested this by simulating real-world detours. They deliberately messed with the planned path at critical points. They tried three main kinds of random disruption. First, road perturbation. Just swapping the correct road in the next step for a different random one, forcing a detour. Second, distance perturbation, telling the model it had traveled a different distance along a road than it actually had. And third, direction perturbation, flipping the direction. So if the next step was go east, they might feed it go west instead.
Okay, so they threw some real curveballs at it. Could the model adapt? Could it figure out it was off track and find a new way?
Not particularly well, unfortunately, especially with the road perturbation. In that scenario, after being forced onto the wrong road, the model only had about an 11.85% chance of picking any valid connecting road for its very next step. It often seemed lost, suggesting its grasp of its current location or the immediate road options wasn't precise enough to recover easily.
Oof, 11.85% is not great. A massive drop from the 83% accuracy when things went smoothly. What's going on there? Why is it so fragile?
It seems its robustness is really tied to the training data. It did a bit better if the disruption happened at a high-frequency turning point, basically, an intersection or junction that appeared many times in its training routes. This suggests its internal map of the road network isn't maybe a fully continuous, globally consistent thing. It might be more like patches of knowledge, stronger around familiar areas, but weaker and more fragmented elsewhere.
So it's good on the familiar highways, but gets lost easily on the back roads. It hasn't seen much.
That seems to be a fair analogy, yeah. It struggles more with the truly unexpected deviations from the patterns it learned. And there was another important caveat they noted. The process of training the model so intensely on these spatial tasks actually caused it to lose some of its original general language abilities. So there seems to be a trade-off. Making it a spatial expert might make it less of a generalist. Finding the right balance between specialized cognition and broad linguistic skill is still very much an open research question.
Right. So for you listening, the takeaway seems to be LLMs are showing these incredible, almost startling abilities to infer spatial layouts and plan routes just from text, which is amazing. But they're not quite ready to be your foolproof self-driving car AI just yet. They struggle when things get messy and unpredictable, and specializing them might come at a cost to their other skills. Wow, what a deep dive that was. We've really unpacked how these large language models can kind of magically build a coherent global map from just scattered local descriptions. Like piecing together a city from whispers, they can predict unseen spatial relationships, their internal states seem to encode actual coordinates, and they can even track their position dynamically during simulated navigation. It's mind-bending stuff.
Absolutely. And if you zoom out, connect it to the bigger picture, it really does suggest something profound. That AI models might be able to acquire complex world cognition, reasoning abilities, just by processing the massive amounts of relational language we use to describe our world. They might not always need explicit pictures or coordinates. Language itself might hold more of the world's structure than we realized, which opens up huge possibilities, right?
Huge possibilities, definitely. But as we saw, the study also reminds us of the limits. That fragility when things go off script. It shows their internal roadmaps might be more localized, maybe more dependent on the specific training data patterns, rather than a truly flexible, comprehensive understanding like a human might have. And that tricky balance between specialized intelligence and general language skill. That's clearly a major frontier for AI research going forward. This research really makes you think, doesn't it? If LLMs can infer such a detailed world map from just fragmented language, how much of our own incredibly rich understanding of the world, way beyond just physical navigation, is maybe built up in a similar way? From the millions of tiny, localized, relational bits of information we absorb every single day, rather than from some perfect, complete instruction manual we were born with. Something for you to ponder as you navigate your own world.